Welcome to The Explainer. Today, we're exploring one of the most awe-inspiring, absolutely terrifying, and just utterly fascinating forces on our planet. We're talking about volcanoes. We'll be using the latest data from the British Geological Survey and the U.S. Geological Survey to unpack exactly how these massive geological engines actually work. But, we're not just looking at the ground beneath our feet. We're going to trace the impact of these eruptions all the way up into the stratosphere, revealing how volcanic forces actually manipulate our global climate in some pretty surprising ways. So here is our roadmap for today. 1. The mechanics of magma. 2. 4 phases of volcanoes. 3. Global cooling from aerosols. And 4. The great CO2 debate. Section 1. The mechanics of magma. Okay, let's dive into this. Before we can even begin to understand those massive mountains on the surface, we have to look at the invisible underground force that drives literally every single eruption. It all comes down to how magma behaves. And the foundational rule here is viscosity. In physics, viscosity is just a fluid's resistance to flow. But in volcanology, viscosity is everything. Think of it as the stickiness of the magma. This one single variable dictates whether magma oozes out gently like pancake syrup, or whether it violently builds up immense pressure until it just explodes. It literally determines the entire shape of the volcano. Think about the two extremes. On one hand, you have high viscosity magma. It's incredibly sticky. Because it doesn't flow very far before it cools down, it just piles up, and that's what creates those classic, really steep mountain slopes of 30 to 35 degrees. And because it's sticky, it traps gas, which makes it highly explosive. Now contrast that with low viscosity magma. This stuff is runny, fluid, basaltic lava. It spreads out smoothly over huge distances, creating wide, very gentle slopes that sit under 10 degrees. Section 2. 4 phases of volcanoes. So moving up to the surface, let's see how this magma sculpts the physical structures we actually recognize. Depending on that stickiness we just talked about, magma basically builds 4 distinct types of volcanoes on Earth: shield volcanoes, stratovolcanoes, lava domes, and calderas. Let's break down what makes each of these so unique with some real-world examples. Take Mauna Kea in Hawaii. That is a classic shield volcano, built entirely by that runny, low-viscosity lava. Because the lava spread so incredibly far, Mauna Kea has grown to an astonishing 9 kilometers high if you measure it all the way from the seafloor. Next up, we have the famous Mount Fuji in Japan, which is a stratovolcano. This is your steep, picturesque cone built by sticky, explosive magma. It actually last erupted back in 1708. Then you have the Souvier Hills in Montserrat, which is a lava dome. The lava there is so incredibly viscous, it barely flows at all. It just piles up into this massive, dome-shaped mass of rock and giant spines right over the vent. And finally, the caldera, like Mount Tambora in Indonesia. When Tambora erupted super violently in 1815, it completely emptied its magma chamber. Without any support underneath, the entire summit just collapsed inward, leaving a massive bowl 6 kilometers wide and over a kilometer deep. No mountain left, just a huge crater. Section 3. Global cooling from aerosols. So we've seen the physical scars left on the ground. But what happens up in the sky? We almost always associate volcanoes with intense, fiery heat. But they can actually chill the planet through a really fascinating 4-step process. Step 1. A major explosive eruption injects a huge cloud of sulfur dioxide, or SO2, high up into the stratosphere. Step 2. This SO2 rapidly condenses to form very fine sulfuric acid aerosols. Step 3 is where the magic really happens. These tiny aerosol droplets act like billions of microscopic mirrors, reflecting solar radiation from the sun straight back out into space, which directly leads to step 4. With way less sunlight actually reaching the surface, the Earth's lower atmosphere simply cools down. To put the sheer scale of this chemical process into perspective, consider this staggering number: 20 million. That is the number of tons of sulfur dioxide that Mount Pinatubo violently injected into the stratosphere during its huge eruption in June of 1991. Imagine a cloud of gas reaching over 20 miles high into the sky. It was literally the largest sulfur dioxide cloud ever observed since we began tracking them with satellites. And the direct result of that 20 million ton cloud? A 1.3 degree Fahrenheit temperature drop. That is how much the Earth's average surface temperature plummeted at the height of the impact. Now, a 1.3 degree drop might not sound like a big deal on a mild Tuesday afternoon, but globally, as an average, that is a massive climate shock. The crucial takeaway here is that a single powerful eruption has the capacity to fundamentally alter the entire global climate, cooling the whole Earth for an astonishing 3 years. Section 4. The Great CO2 Debate. Because volcanoes affect the atmosphere so profoundly, they inevitably spark a major question when we talk about greenhouse gases. People always ask, do the Earth's volcanoes, with all their fiery, earth-shattering power, actually emit more carbon dioxide than human activities? If volcanoes are just so unimaginably massive, do they dwarf human emissions? Well, let's look at exactly what the USGS data tells us. The difference is honestly pretty stark. The highest published scientific estimate for the global CO2 emission rate for all volcanoes combined, and we're talking both on land and deep underwater, is 0.44 gigatons per year. That's the absolute maximum. Now, anthropogenic, or human-caused, CO2 emissions were projected at roughly 35 gigatons for the year 2010 alone. The data is clear. Human activities are responsible for emitting roughly 80 to 270 times more carbon dioxide than all global volcanic activity combined. Volcanic CO2 amounts to less than 1% of total human output. If you're like me and you find gigatons kind of hard to visualize, let's look at a specific event. When Mount St. Helens erupted in 1980, it was an absolute cataclysm. It vented 10 million tons of CO2 into the atmosphere over the course of 9 hours. But compare that to humanity today. Global human activity vents that exact same amount, 10 million tons of CO2, in just 2.5 hours, every single day. Which really brings us to this incredible number, 2.7. It takes a mere 2.7 days for global human activity to emit the exact same amount of carbon dioxide that every single volcano on planet Earth puts out in an entire year. The sheer scale of humanity's ceaseless, everyday emissions thoroughly dwarfs even the most violent, rare volcanic events. So, we've seen how the stickiness of magma builds these colossal mountains, and we've seen how a single, sudden eruption like Pinatubo can just drop global temperatures for years. Volcanoes prove to us exactly how sensitive our atmosphere truly is to chemical changes. So I want to leave you with this final, provocative thought to summarize all the data we've looked at today. If a single geological event can alter the Earth's climate so drastically in just one day, how will our planet adapt to our ceaseless, accelerating output?